Hello everyone, welcome to the second video for section 4.5, continuing on with our study of derivatives and how they relate to the shape of a graph of a function. And in the last video, we talked about something called the first derivative test, and I just wanted to reiterate this. Number one, to highlight that that's the name of it, so it's called the first derivative test, and then also just to review what it entailed. So recall that to use the first derivative test, what we can do is first find the critical points of the function, and then look at the sign of the derivative on each side of those critical points to determine what kind of local extrema we have there. So if we have a situation where the value of the derivative is positive on the left, negative on the right, then we know that we're looking at a local maximum because we have a shape kind of like this one here. If it is negative on the left and positive on the right, then we know that we have a local minimum because now we're looking at a shape like this one. And then if there's the same sign on both sides, then it's neither a local maximum nor a local minimum, and or we can't really definitively say what type of extrema, if any, there are at that point. All right, so that's the first derivative test. Now, I want to go back to early on when we started talking about derivatives. Recall that we talked about how you could take the derivative of a function multiple times. We talked about the first derivative, the second, the third, so on and so forth. And one reason we saw that that was useful was in application problems. If we had a function that gave us, say, the position of something or the distance that something was from a starting point, taking the first derivative gave us that something's velocity at a certain time, and the second derivative gave us the acceleration, which is all fine and dandy, but you may have been thinking since then, Cody, why would you continue to teach us about the second derivative? What does this have to do with anything? Well, let me tell you. So what I have here in this picture is, or on this slide I should say, is a function f, its first derivative, and its second derivative, and graphs of those. And let's first just remind ourselves how the graph of the derivative relates to the graph of the function. So notice, looking at the graph of the first derivative, for all values less than 0, so kind of this period right here, the output values there are positive. And recall that if the output values of the first derivative are positive, that means the function is increasing. And if you look at the values over the same interval over here in the function f, we see that is in fact the case, that for all values less than 0, the function is increasing. If we now look at all values of the function between 0 and 4, of the derivative I should say, notice that there the values of the derivative are negative, which if you recall, again, if the values of the derivative are negative, that means that the function is decreasing. And if we look at the graph then of our function between 0 and 4, we see that that is in fact the case, that the function is decreasing on that interval. Finally, on the first derivative for values greater than 4, we see that it's positive. And when those values are positive, that means the function is increasing, which is what we see over here. Okay, so that's the relationship between the function and its first derivative. Let's now look at the function versus the second derivative. With the second derivative here, we see that for values less than 2 now, the value of the second derivative is negative. And if we compare that to the graph of the original function, we see that we're looking at this piece here. Wondering, what is going on, or what could we say about that portion of the graph? Well, let's hold that thought for a minute. And notice, again, for the second derivative, all values of 2, for all values of 2 greater than 0, the outputs are positive. And again, that corresponds to this portion of the graph here. And what do we see? What is the difference between the orange and the green in the original function? Oh, I know, and I know you guys all just said this. It's concavity, right? Notice that for the green section of the graph here, it looks like it is concave down. And for the orange section, it is concave up. Okay? And so that is what the information that the second derivative gives us, is the concavity, whether at a particular point the graph of the function is concave up or concave down. And if you're not recalling that term concave, remember it kind of has to do with the direction the curvature of the graph is facing. So for on the original graph over here, notice that this portion where I've outlined in green, all the curvature is down. It's kind of like, I think, down like a frown. So that's concave down. And for the parts here where it's orange, that would be concave up, because we see the curvature is facing up. And we can also think that's up like a cup, right? And again, notice that how those relate to intervals over which the second derivative here is positive and negative. Now, one more thing about this. This point 2 right here, where the concavity of the graph changes. So right here, where the graph changes from concave down to concave up. First of all, what do we notice about that point in the second derivative? Well, notice in the second derivative, it is right there on the horizontal axis. So it's actually a value where the second derivative equals 0. So we have at the f double prime of 2 equals 0. Also, what do we call a point like this, where the concavity of the function changes from concave down to concave up, or vice versa? Right, that's called an inflection point. Okay, so the moral of this part of the story is that at values where the second derivative is equal to 0, we will have inflection points of the function. So values where, or places where the concavity of the function is changing. All right. So here is summarization of some of that, and then also an introduction to what we call the second derivative test. So first of all, the first box up there talks about if we have a point where the concavity of a function is changing, then we call that point an inflection point. And then, as we saw, if the value of the second derivative at a particular point or over an interval is greater than 0, that means the function is concave up over that interval or at that point. And similar, if it's negative, then it's concave down. And this is helpful for us because we can then create a new test for helping us to find where local max and local mins are. So notice it says here for the second derivative test that if we find values where the first derivative is equal to 0, and that's important, notice that that's the first derivative, so we're talking about critical points. We're talking specifically the ones where the first derivative equals 0. Then if the value of the second derivative at that point is greater than 0, then that means the function has a local minimum. And let's think about why that would be. If it's the value of the second derivative is greater than 0, we know it's going to be concave up at that point. We also know it's a location of an extrema since it's where the derivative equals 0. And so you can see that would be local minimum. If the value of the second derivative there is less than 0, Then we know we have a local max, which again, thinking about if the value of the second derivative is less than 0, that means we're looking at concave down. We also know we're talking about a critical point here, so we know it's going to be a local extrema, so that's how we know this is a local max. And then finally, if the value of the second derivative equals 0, like it says, the test is inconclusive, but most likely than not, that would be the location of an inflection point, which is why it's neither concave up or concave down there, because it's where the concavity is changing. All right, so let's use this now on this problem. So we have this function v of t equals 2t cubed plus 3t squared minus 12t plus 4, and I apologize if you hear the squeaking in the background. It's my dog playing with his toys. So first of all, we have to find the critical values. So we'll take the derivative here. So v prime of t equals 6t squared plus 6t minus 12. Then we need to take that and set it equal to 0, because for this function it's polynomial, so our critical values will happen whether it's set equal to 0. We solve this, and in this case we can factor this to 6 times t squared plus t minus 2. And I believe that will factor to t plus 2, t minus 1, right? Yep. And so we get that our critical values would be at t equals -2 and t equals 1, right? Okay, so now that we have those critical values, let's use a second derivative test to determine whether or not they're the locations of local mins or local maxes. So in order to use the second derivative test, first of all, we need to find the second derivative. So we had our first derivative was 6t squared plus 6t minus 12. The value, or the formula for the second derivative, will be 12t plus 6. And we go ahead and plug in our two critical values. So we'll evaluate this at -2. If we do that, let's see, we have -24 plus 6, looks like we have -18. And then at the other value, at 1, we would have 12 plus 6, so we'd have 18. So notice for the first one here, we had a negative value, which means that the function is concave down there, which means we're going to have a local max at t equals -2. And then for the value 1, it's the value was positive, so we know that it's going to be concave up, which means we have a local min at t equals 1. Okay. And there we go. All right, that's all for now. Thank you guys for watching.